Hello everyone. My name is Dr. Sok Jun Kwan working at KIST and KIST School. I'm a principal research scientist holding an associate professor at UST, who is a main instructor of this course. Welcome to the lecture 4. In this lecture, I will introduce nanophotonics and nanooptics. In lecture 4, we focus on the nanophotonics and optics. According to National Academic of Science of the USA, this area of nanoscience, called nanophotonics, is defined as the science and engineering of light-matter interactions that take place on wavelength and sub-wavelength scales where the physical, chemical, or structural nature of natural or artificial nanostructured matter controls the interactions. First, I will briefly introduce the principles underlying the light-matter interaction. For this we will recap Maxwell equations and other principles. Second, I would like to talk about photonic crystals, in which light-matter interaction occurs in periodic and regular sub-wavelength structures. Third, I will talk about metal optics and plasmonics. Fourth, I will briefly talk about nanolasers focusing on the random lasers. Fifth, I will talk about nanophotonics applied for the photovoltaic systems. Finally, I will end my lecture with the presentation on the nanooptics and Raman scattering with perspectives on the nanophotonics. To start with, it is very instructive to learn about Maxwell equations. I believe many of you had already learned in detail about these equations. However, I would like revisit the Maxwell equations. The Maxwell equation is composed of 4 different equations on the electric and magnetic field. 2 of them are divergence equations and other 2 equations are curl equation. For your information, Maxwell equations can be written in the form of integral equation. However, I will keep the differential equation expression for the mathematical convenience. I will also go with SI unit systems for the convenience. As you can see in these equations, the divergence and the curl equations show symmetry for the electric and magnetic field. This symmetry implies that the electric and magnetic field are strongly interconnected, and as a matter of fact, they are in one phenomenon such as electromagnetism. Before Maxwell developed these equations, there are a variety of electrical or magnetic phenomena experimentally observed by many scientists. However, it was Maxwell that successfully integrated the scattered information and observations into one mathematical relationships. The real beauty of the Maxwell equation is that its predictability. The equation can be simplified into the wave equation, which in turn provide a solution in a form of wave function. Using experimentally measured physical properties, Maxwell equation predicted the existence of electromagnetic wave with its propagation speed of light speed. This indicates that the light is electromagnetic wave. We will explore in detail each of the equations in next slide. The first equation denotes Coulomb's law. This law describes the diversion of electric flux density in space. Coulomb observed that charges of same sign repel each other, while charges of opposite sign attract each other. He explained this using the concept of an electric field. Every charge has some field lines associated with it. He also found that larger charges give rise to stronger forces between charges. Coulomb explained this with a stronger field or more field lines. By combining Gauss' law and mathematical relationship called Gauss's theorem, we can convert the Gauss law into a relation for Coulomb law. In a similar manner, divergence of the magnetic flux density can be derived. In this case, there is no magnetic charge density and the divergence of the magnetic flux is 0. This is due mainly to a fact that there is no magnetic monopole. Second, Ampere observed that magnetic field can be induced by either changes in electric flux or electrical currents. Using well-known mathematical relationships such as Stokes' theorem, it is possible to rewrite the line integral of magnetic field H around a closed loop C into the curl of the magnetic field over area A closed by the loop. The curl of the magnetic field is equal to temporal changes of electric field density, which is del D over del there plus current density J. Therefore, we can obtain an equation for the magnetic field H and electric flux density D with current density J. In a similar way, Faraday's law can be rewritten with an aid of Stokes' theorem. Faraday's law indicates that the change of the magnetic flux density will induce electric current around a closed loop C. This relation is also symmetric to the Ampere's law. Therefore, it is not surprising that we have two similar and symmetric curl equations. Then, it is natural to deduce some recursive or infinite repeating phenomena from the two curl equations. In particular, you can think of the closed loop on which electric current is circulating. Then, there will be magnetic field induced by the electric current. And the magnetic field is changing over the time, which will be inducing another electric current on the next closed loop. Changing E field results in changing H field results in changing E field, and so on, as shown in this figure. To derive wave equation from the Maxwell equations, we start with the two curl equations. For the convenience, it would be helpful for us to define the relationship between the magnetic flux density B and the magnetic field vector H. Without considering the magnetic polarization, it is possible to write down a simple linear relationship between B and H with a parameter called as magnetic permeability mu. In free space, we will use mu sub naught. We first apply another curl for the first curl equation. Another curl equation we can deduce following equations on the double temporal derivative of electric field density and electric current density J. Using a simplified relationship between the electric field density D and electric field vector E via the dielectric constant epsilon there, it is possible to obtain the final relationship. Now, we can apply well-known vector identity, which will turn the double curl relationship into divergence and Laplacian. And also by assuming neither point electric charge source ρ sub F nor electric current J, we can further simplify the curl equation into this form. For further simplification, we can assume some ideal media with properties of linear, homogeneous, and isotropic characteristics. By linear, it means that the electric polarization vector P is linearly proportional to the electric field. By homogeneous, it means that P is a simple function of E. And by isotropic, it means that P is parallel to the electric field vector. This form is already a wave equation which describes the relationship between the Laplacian of the electric field and the double temporal derivative of the electric field vector. Using a relationship between light speed c and vacuum electric permittivity epsilon sub naught and vacuum magnetic permeability mu sub naught, we can further simplify the wave equation as. And using a relationship between the refractive index n and relative electric permittivity epsilon sub r and relative magnetic permeability mu sub r, we can further simplify the wave equation as. In this equation, we assume the media is non-magnetic, in which mu sub r is equal to 1. We can further simplify this wave equation into final form, where the speed of light is decreased due to the refractive index which is greater than 1. It is important to investigate refractive index of various materials for nanophotonics. Here are some examples of the refractive indices of several materials in the wavelength range from 100 nanometers to 50 micrometers. This range covers ultraviolet, visible light, near-infrared, mid-infrared, and far-infrared including terahertz range. As can be seen from the plots, we can find that most of the refractive indices are not constant for the wide range of the wavelength, and this property of the refractive index is called as dispersion of refraction. Let us think about the complex refractive index. Actually, some materials are transparent to certain wavelength light while some materials are not transparent. This is due mainly to a fact that the refractive index of the materials is a function of wavelength, and there is an imaginary part of the refractive index. For the complex refractive index, we can divide it into real and imaginary parts, and for the imaginary part we can introduce a concept of the absorption coefficient alpha. The stronger the absorption, the less transparent the materials. The greater the absolute value of the imaginary part of the refractive index, the greater the absorption coefficient. By inserting this complex refractive index into the wave function solution, we can find that there are two distinguishing properties of the wave. The first property is traveling, which relies on the real part of the refractive index, as represented by beta here. The second property is decaying, which relies on the imaginary part of the refractive index, as represented by alpha here. As shown in this plot, traveling wave keep the vibration while decaying wave drive the amplitude of the wave diminishes. By combining two properties, we can deduce that electromagnetic wave in the absorbing media will behave as a diminishing wave. As explained in previous slide, refractive index of materials is not a constant and a function of wavelength or frequency of the electromagnetic wave. For example, for insulators, we can observe two distinguishable behavior of the materials, such as strong absorption coefficient in short wavelength and long wavelength regions. For short wavelength region, the strong absorption is due to the electronic transition, which requires higher energy, which is typically corresponding to ultraviolet range. For the long wavelength region, the strong absorption is due to the atomic vibrations, which requires smaller energy, which is typically corresponding to mid-infrared or terahertz range. For typical semiconductors, absorption coefficient exhibit two distinguishable peaks. The first one is smaller energy peaks for the phonon vibration or lattice resonance. The second one is greater energy peaks for the exciton absorption, which requires typically visible light or shorter wavelength light. For insulator and semiconductor, we can derive some important relation between the light frequency omega and conductivity of the materials. The model is called Drude-Lorentz model. We start with expression of electric field with temporal term with oscillation. We insert this expression into the equation of motion of electrons. In this equation, it should be noted that there are drag force term represented by the relaxation time tau here. Using the temporal vibrational expression of the electron's velocity v, we can obtain simplified equation of motion of electrons. By introducing current density vector J, which is equal to the product of electron density n, electric charge E, and the electron's velocity v here. Then, we can introduce another parameter, which is electric conductivity sigma here. The electric conductivity is a proportional coefficient between the electric current density and the electric field. Using these expressions, it is possible to obtain the electric conductivity as follows. For molecules, light scattering due to harmonically driven dipole oscillator. For nanoparticles, we have different mechanisms. First, for insulators we can think of Rayleigh scattering, in which scatter size is much smaller than wavelength of light. Second, for semiconductors, resonance absorption occurs at light energy greater than band gap energy, and we can observe size-dependent fluorescence. Third, for metals, resonance absorption occurs at surface plasmon frequency and there is no light emission. For microparticles with size larger than wavelength of light, there are enhanced forward scattering allowing intuitive ray picture. For microparticles, we can observe Mie scattering and rainbows due to dispersion water droplet. There are many applications for microparticles optics such as resonators, lasers, and so on. Now let's look at nanoscale particles. On the left figure, we can find a typical quantum mechanical properties of semiconductor nanoparticles. For example, this plot is a relationship between the size of silicon nanoparticles and band gap. The band gap increases with decreasing the size, due mainly to a fact that the smaller nanoparticles the larger energy state of standing wave confined in the nanoparticles. By controlling the size, it is possible to obtain different band gaps, from which we can obtain different photoluminescence wavelengths with different colors. On the right figure, we can find a typical relationship between the host matrix refractive index n and the extinction peak of metal nanoparticles. The metal nanoparticles can act as a medium which forms strong near-field given external electromagnetic wave satisfying localized surface plasmon resonance or LSPR. It is possible to calculate the peak position as a function of the host and particle refractive index as well as the size as shown in this equation. As you can see in this plot, the extinction peak is shifted from shorter wavelength to longer wavelength as the refractive index of the host media increases. The extinction peak of metal nanoparticles can be controlled by the size, shape, host media, and metal kinds. This property has been widely used for art about 1500 years. For example, engraved Czechoslovakian glass vase shown in the left picture have two different metal nanoparticles. Firstly, silver nanoparticles cause yellow coloration, while gold nanoparticles cause red coloration. To make the metallic nanoparticle, artist used molten glass readily which can dissolve 0.1% silver or gold. Slow cooling results in nucleation and growth of nanoparticles.